Okay, my name is Lacey Bellinger, and I'm the Director of Collections and Exhibits at the Tallahassee Museum. And we have been offering Museum Mixology bi-monthly on Thursdays at 6 p.m. Eastern Standard Time. I'm really excited about our lineup for this spring. We're moving into May, being focused on Black history, and the 20th of May being Emancipation Day in Florida. So I'm excited about those two programs we've got coming up. I hope you guys are able to attend. This series is designed to be for our adult audience, as you guys know, for Museum Mixology. And I just wanted you to know it's supposed to be a fun learning experience about history, natural science, and wildlife, and occasionally a little bit of true crime. We do have a tip jar set up, so if you are so inclined and want to donate to the museum, I will post the tip jar link in the chat room. We are often discussing topics that are difficult or insensitive, and maybe more so due to the current events. So we do encourage you to carefully read the lecture description and determine for yourselves if your children can attend. Like I said, this is designed for adults, but most of our programs are child-friendly or family-friendly. And today is Earth Day. So tonight we bring you Dr. William Landing, speaking about climate change and ocean acidification impacts for Florida. Dr. Landing has earned degrees in chemistry and chemical oceanography. He joined the faculty in the Department of Oceanography at Florida State University in 1985, and he is currently a full professor in the Department of Earth, Ocean, and Atmospheric Science, which was formed in 2010 via a merger of the FSU Departments of Oceanography, Geological Sciences, and Meteorology. His research interests included the biogeochemistry of trace elements in marine and fresh waters, with emphasis on the effects of biological and inorganic processes on dissolved particulate fractionation, solution speciation, and redox chemistry. I was making sure I didn't skip a line. The development of analytical schemes for studies of trace element concentrations, equilibrium complexes, and redox states in natural waters and the atmosphere, and the chemistry and deposition of atmospheric aerosols and precipitation and mercury cycling in the atmospheric and in aquatic environments. More specifically, Bill and his research team study how natural and pollution dust that is blown off the continents affect marine biological productivity. He is an active participant in the U.S. GeoTraces and Clyvar repeat hydrography research cruise programs and helped lead an international GeoTraces research program in the Arctic Ocean in 2015. These research projects are focused on the impacts of climate change on the chemistry and ecology of the ocean. In addition to these projects, Bill has studied mercury deposition to the Florida Everglades, river runoff of mercury to the Gulf of Mexico, chromium levels in Tallahassee drinking water, and nutrient pollution at Wakulla Springs from the local sewage treatment plant. He has published 100 peer-reviewed research papers resulting from these research projects and brought in over $8 million in external research funding to FSU. Bill has chaired the Leon County Science Advisory Committee for the past 10 years. He is a member of Alpha Chi Sigma, which is an academic chemistry fraternity, the American Chemical Society, the American Geophysical Union, the American Society of Limnology and Oceanography, the Oceanographic Society, and the Union of Concerned Scientists. He is a courtesy professor in the Department of Chemistry and Biochemistry at FSU, an honorary visiting professor with the Faculty of Science at the University of Plymouth in the UK, an associate editor for the journal Marine Chemistry, a former chair of the Geochemistry Division of the American Chemical Society, and a member of the International GeoTraces Data Management Committee. And among all those many other things, he is a musician. I know he would love to talk to you about how he plays the saxophone. So we'll have to get him talking about that when he's done telling us all about Earth Day and how we can help save the Earth through oceanography. So I'm going to turn it over to you, Bill.
Okay, sharing my screen.
Yes.
All right, so you should be able to see my screen now, hopefully.
Yes, you're
Okay, well, first of all, happy Earth Day, everyone. It's a pleasure for me to give this presentation. I'm going to focus on climate change and ocean acidification and the impacts on Florida. A little bit about who I am. Oops, Lacey gave a nice introduction. I got my degrees at UC Santa Cruz and the University of Washington. I spent a year in Sweden on a postdoc and joined the faculty at FSU in 1985, and actually retired February of 2020, just in time for the world to fall apart. But I'm still active in research, and I'm an emeritus professor now in the department. So about climate, climate is what you expect and weather is what you get. And people often confuse those things, especially people who aren't particularly interested in what climate change might be. And they'll say, oh, it's really cold or it's really hot. And what's all this about climate change? Weather is highly variable and chaotic. If you average the weather over about 30 years, that's the climate. Also, global climate change is nothing new. It's been changing throughout geologic time. This graph that you see on the bottom shows the temperature of Earth going back about 500 million years before present, and when it was much warmer. You can see, I hope you can see my cursor. Can you do that? Can you see the cursor? It was much warmer.
Yes, we can see it.
We had warm periods, and then the scale changes. So it's like hundreds of millions of years when in these orange lines when it was much warmer. And then we go tens of millions of years, so like 10 to 60 million years ago, and we went through this thermal maximum. And then it switches to hundreds of thousands of years. So now we've got 500, that's still millions, 5 million years. And then it switches when we see this thing that calls Milankov cycles. I'll explain more about that coming up. That goes back, about 500 to 800,000 years. And then you see the present era where it's going back just 10,000 years as we came out of the last glacial maximum. So, and this is the temperature of the planet. So it's changed a lot over time. It's been warmer, it's been colder, and it's always changing, but it changes on geologic time scales, which are, tens to hundreds to even millions of years. So what natural processes contribute to this? There are quite a few. One of them is called Milankov cycles. It has to deal with the Earth's position relative to the sun. That changes naturally. I'll show that coming up in just a minute. On kind of 100,000-year cycles. We know that the solar intensity can change. The sun is brighter or cooler throughout Earth's history. We have sunspot cycles, which are 10 or 11 or 12-year cycles. And when the sun is brighter, the Earth would be warmer. Another important factor is changes in greenhouse gas concentrations. And the really important ones are water vapor, carbon dioxide, methane, and nitrous oxide. Another important natural process is volcanic eruptions, and actually ash injection into the stratosphere cools the Earth, and we'll see evidence of that in one of the graphs coming up. So those are natural processes that have been going on forever, and they continue to this day. Regarding Milankov cycles, the orbit of the Earth is not a perfect circle around the sun, so it's an ellipse, and the shape of that ellipse changes over time. Also, the angle of the Earth relative to the sun changes. Right now, it's 24.5 degrees relative to the sun, but it changes, and that they call the obliquity. It's like a top wobbling, or it's a wobble in the angle of the Earth relative to the sun. And then there's what's called precession, which is more like the top wobbling. That's where the Earth spinning on its axis actually doesn't spin exactly the same orientation all the time. And those three things come together. And what you'll see is that in the Northern Hemisphere, which is where most of the land masses are, when that Northern Hemisphere on average is a little farther from the sun, the snow and the ice that accumulate in the winter don't all melt. So the next winter, there's even more snow and ice. And the next winter, there's even more. And that reflects sunlight back to space, so that the Earth can cool when the Earth is on average a little bit farther from the sun, it will cool enough to move into a glacial period. And then when these things change, the Earth moves into a position where it's a little bit closer to the sun. And then the ice and the snow start melting. And if they completely melt each summer, then the Earth actually moves into a warmer interglacial period like we're in now. So that's been going on forever. And we actually see data. This is ice core data from Antarctica. It goes back from 800,000 years, so it's almost a million-year-old record. They drill down into the ice and they collect the cores and they section them, and they can extract gas concentrations from the little bubbles that are trapped in the ice. And they can also use isotopes of hydrogen and oxygen to figure out what the temperature was when that snow or that ice accumulated. And what you see is a really good relationship between the CO2 concentrations and the temperature. So when the CO2 is high, it's warmer. And you just see that pattern repeating over and over for the last 800,000 years. This is an expression of Milankov cycles. And you can see this kind of 100,000-year periodicity to the record. So the bottom line is there's two things to get from this diagram. One is that the maximum CO2 during these interglacial periods is about 200 to 300 or so parts per million. And those are the maximum, which these blue line you see here, it never really goes up above about 300 parts per million. And when it's high, the Earth is always warmer. Right now, we've just, this is actually an old image, but the CO2 in the atmosphere right now is 420 parts per million. So it's well above anything that it's been in the last million years. All right, so how much of, here's a graph. This is controversial, but it is supposed to show what we've observed for global warming going back to about 1870 or 1860 or so. And you see the temperature, it fluctuates a lot, but starting about 1960 or so, it looks like it's been increasing pretty rapidly, almost 2 degrees Fahrenheit above what the average would have been. So this is the difference in over the average. So the average is converted to 0, and then the change is what you see over that average. So it's about almost 2 degrees Fahrenheit. How much of this change, if it's real, is actually due to natural versus anthropogenic factors? Right. So we looked at Milankov cycles. Well, right now we're in an interglacial period, which should be a stable climate condition. We're not. The Milankov cycles can't possibly cause this kind of temperature change in 50 years. That would never happen. Solar intensity, if you look at this bottom graph, they're actually trying to show you how these different factors can change the temperature of the planet. And the red is the solar input. So you can see over time, get my cursor back, yeah, solar input cycles on these sunspot cycles. Sometimes it's a little warmer, sometimes it's not. But the impact that has on global climate and global temperature is really quite small. The blue line is what you get from volcanic eruptions. And we have a really good record of volcanic eruptions as long as people have been paying attention to it. We had a couple of big ones in the 1980s. And you see they actually cool the Earth. And then if you try and put together all the what we call the anthropogenic or human cause factors and look at those, that's this blue line. And that blue line parallels what we've observed. So it appears to support that there is warming and that's being caused by humans, by human activity. Another thing that you might hear, and I've heard it said that, CO2 is coming out of volcanoes and it's not coming from human activity. And it turns out that humans are emitting about more than 100 times more CO2 than volcanoes. So if you hear that, that's wrong. Volcanoes do not emit more CO2 than humans. And in fact, volcanic eruptions help cool the Earth. All right, so if you say what climate change processes could be affected by our now quite large human population, almost 9 billion people. And that what's important is to ask what's changed, all right? The natural cycles do change over time. but we haven't created, the new ones haven't sprung up. They've been going on forever. The question is, what's changed? And what we'll see is that greenhouse gases, which include carbon dioxide, methane, and nitrous oxide, they're going up as a result of human activity. And these higher greenhouse gas concentrations should make the earth warmer. Agriculture and deforestation. Well, trees and forest soils are sinks for carbon dioxide. We've had net deforestation for hundreds of years now, and we're disturbing the carbon balance in soils as well. Cows, we grow a lot of cows and we grow a lot of rice. Those are sources of methane. And we use a lot of fertilizer now to feed the growing global population, and that produces some nitrous oxide. So human activities are definitely increasing the concentrations of CO2, methane, and nitrous oxide. We also create more dust and air pollution. And it turns out, this is something I work on in my research, is that desert dust actually helps fertilize the oceans. And then the ecosystem takes up carbon dioxide. So that if this weren't happening, the CO2 levels in the atmosphere would actually be higher. And the oceans have actually absorbed a lot of the carbon dioxide we've emitted, about 30%. So the oceans are trying to help us. The CO2 in the atmosphere would be even higher if it weren't for what's going on in the oceans. Another thing is that air pollution, the aerosols actually reflect sunlight, and that helps cool the earth. Both of these factors would help cool the earth. But these are things that humans have changed. So it all comes down to what we call the greenhouse effect, which I say it's like the parked car effect. Everyone's experienced this. The sunlight passes through the windows, but the infrared heat can't get out, so the inside of your car gets warmer. The Earth has always had a greenhouse effect. It's what makes the Earth habitable. It allows us to have liquid water. It allows us to have to exist as far from the sun as we are. But fossil fuel burning puts excess CO2 into the atmosphere and the oceans, and that should change global climate. It's expected to get warmer, and the excess CO2 causes ocean acidification. So here's a record of CO2 in the atmosphere, this upper image from a variety of places, measurements from ice cores at the South Pole, but then actual real measurements that started about, these black symbols started about 1960 or so. We actually started making measurements. And what you see is that the CO2 before about 1700, before the Industrial Revolution, was about 280 parts per million, which the ice core records show us is what it is, has always been during interglacial periods. So this rapid increase, what's causing this rapid increase? Well, you can look at how much carbon we've burned. So we can look at the total here this is per year, but you can see starting about 1850, we started burning fossil fuel. And the amount of CO2 that's been released from that can actually be calculated, and it actually agrees with what's in the atmosphere. If we compare how much has gone into the ocean, how much has gone into some additional plant growth, because higher CO2 helps plants grow a little faster sometimes. The bottom line is we can prove that most of the CO2 is from fossil fuel burning. So that's not an argument. That's not if you hear people argue that's not true, no, we can prove that this increased CO2, the vast majority of it is from fossil fuel burning. All right, is it really getting warmer? Well, here's a record that goes back 1700 years, starting about 300, the year 300 AD. And you can see, again, the difference from the average. You set the average to 0 and you look, so it's a little cooler here, a little bit warmer here, a little bit cooler here. And then you see what's happened as we get into the modern record. It looks like it's getting much warmer. So it looks like it might be getting warmer. Is that due to higher CO2 and other greenhouse gases? Well, geologic history tells us that it should get warmer as the CO2 increases. What other evidence do we have that it's getting warmer? Glaciers around the world are melting much faster recently than they did even 50 years ago. They're retreating and melting much faster. In the Arctic, we see that the extent of Arctic sea ice, we're getting nearly ice-free summers. It's going to open up the shipping lanes in the Arctic. That's a big issue. We're seeing plants and animals are responding to climate change. They're moving away from the equator and they're moving to higher altitude to find their ideal temperature zone. And we can see that happening both on land and in the oceans. Finally, the oceans are warming up. We can actually measure the increase in temperature in the oceans as a result of this. So we have lots of evidence. You could ask, well, what's the future going to look like? And these are complicated diagrams, but these are estimates of CO2 emission from fossil fuel burning going back in time to going with this one starts in 1980, but we know how much was emitted because we have records of it. You get to 2100 today, and then you say, what's going to happen in the future? If we stop burning fossil fuel now, or if we decrease our use of fossil fuels now, follow this blue line. All right, if we follow this blue line, we actually get to about 2070. We actually have to start removing CO2 from the atmosphere. And that's to keep the temperature change down. It shows it right here, between about 1 and 2 degrees centigrade. That's how much warming we're going to get, even if we do what this blue line says. We're going to decrease fossil fuel emissions, and we're going to start actually recovering some of that CO2 from the atmosphere out to 2100. We're still going to get a temperature change of about 1 to 2 degrees. The red scenario is what they call the business as usual scenario. That's if we just keep burning fossil fuel and don't do anything about it. And we're going to see concentrations of CO2 in the atmosphere that might exceed 1,000 parts per million. We'll see temperature change of about 3 to 5 degrees, which is about 7 degrees Fahrenheit. And you see lots of lines here. That's because they run lots of different models with there's lots of options. These models they're imperfect and they're showing the uncertainty in the model calculations because we just have an imperfect understanding of how climate really works and all the factors that affect climate. But the trend in every cluster of lines is the same. And the lower graph just shows what the temperature change would be depending on which scenario. So as I said, the scenario where we stop burning or we really cut back on fossil fuel burning now, we're still committed to about a 1 degree centigrade change. And if we don't stop burning fossil fuel, we're looking at about a 4 degree centigrade change, which is about 7 degrees Fahrenheit. So that's what people are worried about. All right, so how would this affect us? Well, you probably have heard, we might get more severe weather events, which include things like floods, droughts, heat waves, wildfires, hurricanes. You know, floods and wildfires droughts and floods seem to be opposite things. Well, some areas are predicted to get wetter. Some areas are predicted to get drier. The models are imperfect, but this is what we think should happen. We should see sea level rise because of melting glacial ice, and I'll talk about that more coming up. But that'll lead to coastal flooding, loss of property, insurance costs. We might see increases in disease because we'll have less clean water. We'll have more ticks and mosquitoes spreading disease. Things that a lot of people are worried about is the food supply. The population on the planet is growing. 3 billion people a day live on rice. If these crops start to fail because of climate change, that's going to be a real problem. Societies and governments be destabilized by climate change. And that will raise the cost for our global military presence. It will cost us money, even if it doesn't affect us directly, because we'll feel obligated, as we always have been. We have some sort of global military presence. That would have to cost more. And finally, we're consuming this natural resource. Fossil fuels, we use them to produce all kinds of things that we use in our daily lives, like plastics and polymers. should we just burn it all, or should we try and preserve it? And what if impacts do we expect in Florida? The oceans should warm up and expand because warm water occupies more volume. Glacial ice is melting. That'll raise sea level, and that'll cause more coastal flooding. Hurricane frequency and intensity might increase. We know that, and I'll talk about all these things in a little more detail coming up. The oceans are getting more acidic. That will affect our coral reefs. And as I mentioned before, ecosystems are already responding to what looks like global warming phenomena. All right, so sea level rise. What do we know about that? This record here shows the sea level rise as we came out of the last glacial maximum 20,000 years ago. Okay, so here's the last glacial maximum 20,000 years ago. Sea level was 120 meters below what it is today. That's 400 feet. That's why Wakulla Springs, which currently is a river, that spring that enters and creates this river, the entrance to Wakulla Springs was exposed. The water was running out, but or animals went into the cave. That's where the mastodon bones come from that we have in our museum. And then, where's my cursor again? There it is. So as it started warming up, sea level went up, and there's pulses where sea level rose quickly. And then about 6,000 years ago, it stabilized. Okay, so we got into the current interglacial period, and sea level stabilized basically where it is today. If we melt the rest of the glacial ice, sea level would go up another 70 meters, or about 230 feet. That would be catastrophic. All right, is sea level really going up faster? And this record goes back to 1880. You see sea levels pretty not changing a lot, and then starting in about 1920 or so, it looks like it's increasing. So sea level looks like it's going up. There's lots of variability in this. It's actually very hard to measure sea level change because the tide gauges are in different places. As you came out of the last glacial maximum, there were huge ice sheets over North America. When those melted, the land actually started rising up, which would make sea level look like it was going down relative to the ocean. There's lots of factors that affect sea level rise, but it looks like it's going up. And what would that do? So estimates vary, but by about 2100, we could see a 3 to 6 foot increase in sea level. And that would affect every city on the planet. Low-lying coastal cities, New Orleans, and I just listed some Florida cities that would be underwater or heavily impacted by rising sea level. And there's actually a website where you can zoom in to where you live and actually start raising the sea level to see when does it flood your yard. And so I've had my students do that, students from Tampa or Miami or Jacksonville or Fort Myers, and actually go play with this model where they could watch sea level rise and tell me when it would actually start to flood their neighborhood. But this is billions of coastal property in Florida alone. And it's estimated that if we don't do anything about this, this is easily going to cost us billions of dollars, hundreds of billions of dollars annually in lost productivity. All right, what about hurricanes? Will there be more hurricanes? The models, the science is not clear on that. I'd put 2 question marks there because it's not clear that we'll get more storms. What is pretty well established is that the intensity of those storms will go up. So I put the red arrow there. We think most of the meteorologists that I work with agree that hurricane intensity will go up. Storm surge. Well, if we have sea level rise combined with more intense hurricanes, we're going to get more coastal flooding. Hurricanes in a warmer environment are able to hold more water vapor, so we'll get more rain and more freshwater flooding. People look at the hurricanes that flooded Houston a few years ago as evidence for this, but that's really weather. It's not climate yet. But these things look like they're happening. And I want to thank Allison Wing, one of my colleagues in the department who studies this problem. All right, what about ocean acidification? I'll describe what it is, what does it matter, why does it matter, and what can be done. It turns out CO2 is very soluble in water, extremely soluble. It makes carbonic acid, which is a weak acid, but still lowers the pH. So if you raise the CO2 level in the atmosphere over the water, more CO2 goes into the water. It happens very quickly. What we know is that organisms like corals, some phytoplankton and some zooplankton, they precipitate calcium carbonate from seawater. And I've shown the chemical reaction here. Calcium ions plus carbonate ions forms calcium carbonate. That's the basic structure of a coral reef is this solid calcium carbonate that they precipitate. When the ocean's more acidic, it lowers the carbonate concentration. And that makes it harder to form calcium carbonate. So organisms currently don't have to expend much energy at all to make calcium carbonate. But if the carbonate concentration goes down too much, then they'll have to expend more energy to make their calcium carbonate. So this image shows what would happen if you take ocean acidification and you combine it with higher temperatures. So here's a coral reef with at 375 parts per million CO2 and a 1 degree temperature change, and the reef looks pretty healthy. You raise the CO2 to 450 to 500 parts per million and add another degree, so you got plus 2 degrees centigrade warming. It's not quite as healthy. And then if you go above 500 parts per million and a greater than 3 degree temperature change, that you see the reef looks dead. And so predictions have been made that the corals are going to become increasingly rare, and we might lose them living coral reefs by 2050. Biofouling algae would become more abundant. And because the coral reefs support so many animals, you get a decline in biodiversity. And the impact to Florida is that the Florida Keys, the reef, offshore reef in the Florida Keys is protective. It protects those islands. They still get hit hard by a hurricane, but without that protective reef, they would be hit even harder. And also, there's phytoplankton that precipitate calcium carbonate, and I point out that half of the global photosynthesis occurs in the ocean by phytoplankton. The oxygen in every other breath you take is produced by phytoplankton in the ocean. And these particular organisms here, there's a electron micrograph image of one of these called a coccolith. They precipitate calcium carbonate. That helps remove CO2 from the environment. It also makes organic matter for the food web. So that's if these guys are no longer able to function, we lose their ability to take CO2 out of the atmosphere and their ability to make organic matter. So it'll have an impact on the marine food web. And this is, you can actually see their blooms from space because they're whitish, and they grow in huge quantities when the conditions are right. And so you can actually see them from space. All right, so how do we deal with climate change, with ocean acidification? You could say, well, the species will adapt, but adaptation is when species evolve genetically over many generations. And that means that you'd have to have a really fast generation time relative to the rate of pH change in order to adapt. Right now, the rate of ocean acidification is about 100 times faster than we have any evidence for happening for the last tens of millions of years. So really, the only solution to ocean acidification is we have to lower the CO2 in the atmosphere. We cannot let it continue to rise the way it's going now. All right, you may have heard that all of this is just a hoax perpetrated by climate scientists to enrich themselves. I'll point out that our salaries are nowhere near those of the CEOs or the Koch brothers. Scientists rely on their reputation. If we falsify our data or our conclusions, we could be expelled from the field. We would lose our credibility. We would forfeit our jobs. Why would we take the risk? And why would hundreds and hundreds, even thousands of climate scientists who all agree that climate change is occurring and that human activity is responsible for a lot of it. Why would we falsify that and take the risk? We'd lose our jobs. And I pointed here, if I don't actually work on climate change directly, but if I did, and if I were right, and if my colleagues thought that I was really brilliant and worthy of it, I might win the Nobel Prize. And if I did, that'd be worth about $600,000 after taxes. So follow the money. Who's making money by extracting and burning fossil fuel? The two largest oil companies, Exxon and Chevron, $70 billion in annual profit in 2012. They're making huge amounts of money in dealing with fossil fuel. You also would, if you look into it, there are many climate change skeptics, and many of them are funded by the fossil fuel industry, and they're using the same strategies the tobacco company used back to fight the limitations on smoking. So it's you know, just follow the money. What about alternative energy? You've heard a lot about that. You've heard a lot of stuff that says, well, it's not really going to work for us. But I just wanted to show this little video that exposes the misinformation, what I would call willful ignorance on the part of Fox News. So I'm going to stop sharing for a moment to show the video. Hopefully you can hear this and see this.
It's a source of energy that's becoming cheaper. We all know it's cleaner, and more businesses are starting to take notice. We've got to double down on a clean energy industry that's never been more promising. Doubling the clean energy we use.
In investing in clean energy.
To jumpstart a homegrown clean energy industry.
So remember when President Obama touted the future of green energy and pumped billions of tax dollars into solar power production? Well, today the industry's future looks dim as investments into green energy are beginning now to dry up.
Fox Business Network's Shivani Joshi joins us right now to explain. So as the subsidies dry up, so does the business, because?
Well, because there's, you know, tons of jobs, and the entire industry is reliant upon these billions of dollars, and we know where those billions have gotten us. I mean, according to my research, 1/10 of the grid comes from solar power. So you think about the money that's gone in, billions, and the output, almost nothing, right? And so now Wall Street, this is a big business issue, and what everyone is talking about is what's going to happen with the solar industry, what's going to happen with those billions, what's going to happen with those jobs that he said they were going to be created, and clearly the nation is in need of jobs. They're just not coming from solar right now.
Sure. So if we take a look at the failed subsidized solar companies, there are, unfortunately, a lot of them. Solyndra, everyone remembers that.
Well, this is not a good track record here, certainly, and we know what the checkered past has been for President Obama and his statements about the solar industry and what the subsidies are providing. The one thing I want to make mention, I mean, subsidies in and of themselves are not a bad thing. We see it happen in the technology industry. It happened with nuclear, even happened with the oil industry. But the problem is that the solar industry has never proved that it can take the training wheels off of additional funds and run on its own. Now people are saying, well, solar may be dead in the water. What's going to happen with nat gas? I mean, I know you guys know this very well. We've got 100 years of energy. It's much cleaner than coal, out of producing 50% less CO2. There's lots of great reasons and jobs, frankly, right? So many people are talking about on Wall Street and the business industry, okay, let's take our focus off of solar, let's move it to nat gas, and let's get this economy going because it's about time.
Because that's really what we have a lot of. But, you know, the United States simply hasn't figured out how to do solar effectively and cheaply. You look at the country of Germany, It's working out great for them.
It is working out great for them, and we just have to figure out where we want to be as a nation. I mean, the problem is that with the solar industry, you have the Chinese coming in and undercutting the markets, and so that's what the subsidies were doing. It was making us more competitive with the Chinese. Well, then they start to cut prices again, and then we start to throw more money. That's not a viable business solution.
What was Germany doing correct? Are they just a smaller country that made it more feasible?
They're a smaller country, and they've got lots of sun, right? They've got a lot more sun than we do, and the problem is it's a cloudy day and it's raining, you're not going to have it. I mean, this nation is vast and beautiful in its makeup. In California, it's a great solution. Sure. Here on the East Coast, it's just not going to work. So you have to have a little bit more of a mixed solution. Of course, nat gas is a big part of that too.
Because we got plenty of that.
Yep.
All right, Shivani, thank you very much for joining us today.
Thanks.
The business.
All right, I'll go back to my presentation. I hope everyone could hear that and see that. So they claimed natural gas is better, and they're obviously ignoring the problems with fracking that fracking causes. They say there's more jobs in natural gas, so more jobs. Let's get the economy going. They argue that these subsidies for alternative energy development were a waste of taxpayer dollars. Finally, they said it's more sunny in Germany. Well, hang on. I have to go back to this. Okay. So this is solar potential. Is it really sunnier in Germany? Well, no. Germany has the solar potential of Alaska. And, oh, we can't do it in the Northeast because it's just not sunny enough. Well, most of America has solar potential similar to Spain. And of course, there are places where the solar potential is much higher. So to argue that it's much sunnier in Germany is just insane. What about jobs? Well, in 2016, jobs in electric power generation in the United States, solar, 374,000 jobs. That's about 3 times more than all the jobs in all the fossil fuels. So there's oil, natural gas, and coal. About 3 times more jobs than in fossil fuel jobs. So if you want to be a job creator, you don't go into fossil fuel. Natural gas is a limited resource. So they argued about sustainable business models. Well, relying on a limited resource for energy is not a sustainable business model. Solar energy is becoming more and more sustainable. The payback now for at current energy prices, if you put solar panels on your house, you could expect to save enough money to pay back the cost in about 10 or 12 years. And that payback period is dropping. Finally, the solar energy subsidies were not a failure. And in fact, Solyndra, which is right down here at the bottom of this little arrow, that failed. But the Department of Energy had a loan program for alternative energy research, and 98% of those were successful. About 2% were unsuccessful. And it was, so the loss, and if you look back at that table that they showed in their video, it added up to about $1 billion. Yeah, it sounds like a lot, but it's really not. Out of 35 billion in loans, 98% of that was successful. So, and finally, was it a waste of taxpayer dollars? Right now, this is data from 2011. So it's probably changed since then. I'm sure it's changed. We subsidize the fossil fuel industry in many ways to the tune of about $500 billion a year, compared to the less than $1 billion that was resulted from failed DOE alternative loan guarantees since 2009. So again, follow the money and you see that the fossil fuel industry is heavily subsidized. That's your tax dollars compared to the failed alternative energy loan guarantees. They conveniently neglected to discuss that in the Fox News interview. All right, so what can we do? the best action is to reduce fossil fuel emissions. That's clearly what we know that this is what we should do. It's hard to do, but it's getting easier to do every day. We can support policies to reduce carbon dioxide and other greenhouse gas emissions. We can move to renewable energy sources as soon as possible. One of my colleagues, Munir Humayun in my department, had an undergraduate do a spreadsheet calculation that showed that the city of Tallahassee could go 100% solar and save tens of millions of dollars a year, and do it by 2035 if they invested now some of the money that they will save when they no longer have to buy natural gas to produce electricity for the city. It's great that the city is building the solar farm out at the airport, and they should do more of it. You can reduce your personal greenhouse gas footprint. There's things you can do, and I'll talk about those in a little bit. The main thing is to educate yourself on the facts and the science. Many of these things, there's still lots of uncertainties. Science is often messy and uncertain, but there are some things that we're quite sure about. And finally, vote. Elect people at all levels, local, state, and federal, who do what you want them to do. Well, the people have a voice. One thing that I've given this talk before to the Rotary Club, and I said, how many of you guys in the audience sell insurance? And a bunch of hands went up. And I said, all right, we are willing to spend about 1% of the replacement value per year to protect our homes, about 2% per year to protect our cars from catastrophic loss. Right? So you've convinced us we need to buy insurance to protect against catastrophic loss. Well, it would be great if the climate change predictions are wrong. What if we're wrong? And it would be great if the worst that could happen from climate change just doesn't happen. But what's the replacement value of our environment? Like what is it worth by insurance to insure against the worst potential outcomes? And 1% of U.S. gross domestic product would be about $200 billion per year. That alternative energy loan program was $35 billion as spread out over years. I mean, if we put $200 billion a year into alternative energy for the country as insurance against climate change impacts, that would be a lot of money. We could do that. And the bottom line is, there's no plan B. There's no planet B. We're stuck with what we're doing to this planet, and we're going to be stuck with it for hundreds of years. Isn't it prudent to think about spending a little bit money now, some money now, to protect against the worst possible outcomes? If you haven't done this, it's fun to go to one of these carbon footprint calculators. I list a couple here. I think both of them, are still active links. But if you just Google carbon footprint calculator, you can find lots of places where you can put in how you live your life. And it will tell you what your greenhouse gas footprint is. And by making modest changes in your lifestyle, you can reduce it by 20 or 30 or 40%. It's kind of fun to do that. I encourage everyone to give that a try. Some of the obvious things, change to light bulbs that emit less heat. So LED light bulbs, you save about 50% a year. You can turn off your electronics when they're not in use. Clearly, using public transportation or carpooling, that's a way to, if you don't drive your car one day a week, you've just saved 20% in fuel costs for your car. Laptops versus desktops. Laptops use less energy. Water. A lot of people buy bottled water. Bottled water costs more than gasoline. So you can buy Tallahassee water, which costs about 2 cents per gallon, and you can purify it if you want, but it's actually quite pure coming right out of the ground. You can adjust your thermostat and use ceiling fans. Ceiling fans are much cheaper to run in terms of electricity consumption than air conditioning. Food transportation is a huge cost and a huge source of carbon dioxide emission. Try, if you can, buy locally grown food. And finally, embrace these alternative energy solutions. 4% of the Florida land area could produce 100% of our energy use for all purposes, including transportation. And, we're supposed to be the Sunshine State. We have no statewide solar energy program. And we've seen other states do it very successfully. California has done it successfully. But we're the Sunshine State. We should be leading. Finally, follow the science. There's lots of, your tax dollars are NASA and NOAA, the Department of Energy, even the Department of Defense has useful information about climate change and, showing you the science behind climate change. And I just found this one recently. This is from the National Academies on climate, and they're actually going to have in a couple of days a summit on our planet, our future. So there's just a huge amount of information out there. Here's a thing on solar geoengineering. That's something that's coming up. I think it's we may have to do some things like that. They talk about injecting aerosols into the stratosphere to reflect sunlight and cool the earth. That'll have a global impact, but that's what people are working on. Thank you. That's it.
Okay, we'll wait a few seconds here to see if anybody's got any questions. Thank you so much, Dr. Landing. Benina would like to know, is it true the energy created by solar panel must be used within a few seconds or it is lost?
No, the battery, you can do battery storage. That's something that's coming up now. Batteries, that's an additional cost, and you have to factor that in. The other thing that can be done with solar, and I've seen a few places doing it, is use the solar energy as it's being generated and use it to do electrolysis of water, which produces hydrogen. And you can store the hydrogen gas and use that as a fuel at night or when the sun's not out. So you could use solar energy to pump water uphill. If you had topography, you could pump water uphill during the day and run it downhill at night through a turbine. So there's a bunch of ways you can use the energy in real time. But with battery storage, that's the plan that this undergraduate did for the city of Tallahassee involved basically everyone by 2030 or so getting an electric car. And the idea would the city would help subsidize that. So when you replace your car, you get an electric vehicle, you charge it during the day when the sun's out, and at night you'd plug it into the grid and you'd run the city at night using a distributed set of batteries in electric vehicles. I mean, there's so many ways you could do it, but it's true that, you have to figure out a way to store the energy, but there's plenty of ways to do that.
And Nancy says, thank you for a great presentation. She'll definitely check out her carbon footprint.
It's really fun to do. There's a bunch of different ones, and they have lots of different things that you can play with, like how many people are in your house, and you'll see things that really blow up your carbon footprint, like flying internationally, flying on a jet plane. That really blows up your carbon footprint. But there's a bunch of ways you can reduce your carbon footprint very easily and without really changing your lifestyle at all.
Mm-hmm. Okay, my neighbor installed a solar water heater and is now having problems with someone to service the unit and solar panels. Is this a common issue?
It's a shame that they're having trouble, because a good solar installer should stand by their product and be available to help service it. The industry at that level is maybe still developing. I know there are a couple of solar installers in Tallahassee that I think, I don't want to advocate any one company or another. One of them has been around for several decades. I think they should be reliable, but yeah, I mean, that's unfortunate. It shouldn't be a problem. And again, if you imagine that the solar industry is really kind of just getting off the ground, it's growing rapidly. But, you know, imagine that you'd gotten the first oil-fired or gas-fired hot water heater, you know, 100 years ago. You know, you might have had trouble with that too. So stick with it. It should get better.
Okay, Faith would like to know, do you imagine we could change cultural habits via food consumption?
You know, it's not clear how much those things help. It's not clear that we actually have to do that. Again, the plan that was developed for the city of Tallahassee has been presented to the city commission as well. We would be able to run the entire city on solar and not have to change our energy consumption patterns. And so in theory, you know, people say, oh, we can't go to alternative energy because we'd all have to go back and live in teepees in the forest because we can't generate enough energy. And the answer is that's just not true. It is possible that we could, you know, the biggest impacts are from burning fossil fuel. We just need to cut down the amount of fossil fuel we burn. Solar is really, there's places where wind is working great. Florida's not a particularly good wind energy state. We can't do hydroelectric very well because we don't have enough topography. You know, alternative energy is really the solution. And if we do it right, we don't actually have to revert to the Stone Age and start living in caves or teepees.
Okay, Benita would like to know, is thermal heating and cooling also being considered? It can be. Thermal cooling, of course, we use here in Tallahassee. I mean, the Florida State University, for air conditioning in the summer, pumps up cold groundwater using pumps, which are relatively efficient to run. They pump up cold groundwater, they use it to cool the buildings, and then they pump the water back down, and it's slightly warmer, but it doesn't hurt the aquifer. So we use thermal cooling already here in Tallahassee. Geothermal heating, of course, requires a source of geothermal heat, which we don't really have, but that is being used other places. All of those things will help. So yeah, I mean, those are probably more limited in terms of, you know, because the sun is shining, you know, somewhere on the United States every day. In some places it shines all day long most of the year. Even in Florida, yeah, okay, the rainstorm comes over and the solar panels, the output would go down for while they're shaded and of course at night. But there are solutions to that, to capture the energy and use it when the panels aren't working properly. So that's true of all these alternative energy sources. And I should also add, we don't stop. We can't stop using fossil fuel immediately, and even very quickly. We would have to transition away from fossil fuel to alternative energy. So we're not talking about shutting down all the power plants tomorrow and trying to live without that energy. The bottom line is we have to transition away from fossil fuel as fast as we can. And as fast as the alternative energy sources can replace the energy, that's how we should do it. What does that transition look like? I mean, in terms of time, what do you think?
It could be done. I mean, communities and businesses are saying that they're going to go to net zero emission by 2035 or 2050.
Oh, okay.
The models for climate change show that we need to cut back our fossil fuel burning really starting now. And if you go back to that one image, it showed slowly declining CO2 emission from fossil fuel use, and that would keep the temperature change at an acceptable level.
Mm-hmm. Do we have any other questions? I'm following the City of Tallahassee's progress on clean energy. Do you know what their backup plan would be if solar panels were wiped out? Also, I understand some components of solar panels are made with byproducts or products of fossil fuels.
That's a good question. Yeah, I mean, a catastrophic hurricane could rip up the solar farm. I mean, that's just, I mean, yeah, you just have to live with that. And be prepared to, like I said, we don't shut down the power plant that we have that burns natural gas. We just keep that there as a backup. And so that if something happens and the solar system completely fails, the lights don't go out. But, they're designed and installed to withstand certain wind levels. So, I mean, if you put them on your roof, they're supposed to withstand hurricane force winds. The installer is supposed to put them in there to do that. So I think, so that, there's a risk, sure. But with regard to the components that go into solar panels, what you need to think about is it's like a cradle to grave problem. From the time you imagine producing anything till the time you finally dispose of it in some environmentally correct way, how much CO2, what's the greenhouse gas footprint of that thing from the time you start to make it till the time you finally dispose of it? That's what you need to consider. And so, yes, there is no product that currently doesn't require some energy. And right now, most of that energy is coming from fossil fuel burning. So even when we build solar panels, there's some CO2, there's some greenhouse gas footprint of building the panels. But then they start producing energy from the sun. And they quickly overcome that initial cost of greenhouse gas to produce the product. The same thing with a hybrid vehicle. A hybrid vehicle burns much less fuel, but there's a greenhouse gas footprint to produce the vehicle and to produce the batteries. So, I mean, those are things that you could do right now. You're seeing like hybrid vehicles. They're big. They used to be tiny little, little cars, and now you can get a hybrid engine in even a big pickup truck. Well, then get a hybrid engine the next time you get a car, or get an all-electric vehicle, because they're available. They're becoming more available. And even if the electricity still comes from fossil fuel burning, it's more efficient to use electric vehicles where the electricity is generated at a central location like our power plant than it is to burn fossil fuel in your individual car. So all these things make a difference.
I think we're done on questions, maybe? Oh, nope, there we go. What the heat that's generated from the solar panels, what effect does it have on heating our environment?
I think it's less because they're somewhat reflective. So they're reflecting some of the sunlight that hits them. Plus, they're absorbing the energy and using it to create electricity. Whereas if that sunlight falls on the soil, it would warm up the soil more than it would warm up the solar panel. I think heat pollution, it's not I'd have to look into that. I don't think that's considered to be a problem. I don't think the heat pollution from gathering solar energy is something that is significant enough to worry about, but I could be wrong.
Okay. Anybody else got something? No? we are done with questions. So thank you so much, Dr. Landing. I really appreciate you being here and joining us. I know I harassed you while you were out on research on the ship, and finally I got you home and was able to get you booked to speak with us, but I truly appreciate it. And I hope everybody's able to join us in 2 weeks when we'll be talking about Black history with Dr. Kimberly Brown Pelham, who happens to be the model for the Rosa Parks statue. So I think that's an interesting tidbit about her, but she may not talk about that very much. But regardless, I hope to see you all guys, all of you in a couple weeks. And everybody take care, stay healthy out there. And
thank you.
Thank you,
for listening.